Question 3 was asking about the partial derivative and where it appears in one of the governing equations for fluid flow. It's a second derivative. The only second derivatives that we have in the governing equations are viscous terms. So it's definitely a viscous stress term. Right there. It's one of these ones that fits into this equation. They've all got di2w with respect to something. There's a di2w di-x squared term, a di2w di-y squared term, and a di2w di-z squared term. Those show up in the Navier-Stokes equation for momentum in the z direction, because we're interested in all the changes in the w velocity, which is the velocity in the z direction. So which equation? A momentum equation or a Navier-Stokes equation in the z direction. So it was important to get the momentum and the direction right. What does it represent? Explain with a two-dimensional diagram, including both important axes of the coordinate system. Well, the two important axes are z, the direction of the velocity component, and x, the direction in which it's varying. It represents viscous stresses or forces in the z direction. And what's happening here is if we draw a little square box, there's shear stresses on these faces, the ones that are pointed in the x direction. There's a shear stress here on this side due to the fact that there's a velocity gradient there. So if di-w di-x, if w is increasing with x, then di-w di-x is positive. Multiply that velocity gradient times the viscosity and you get a shear stress going in that direction on this side of a little block control volume. If we look at the other side, there's a shear stress going in this direction. Again, if di-w di-x is positive, it'll be slower over here, faster over here, and the stress will be pulling back like this. Multiply by viscosity to get a shear stress. Now the net force acting on the control volume depends on the difference between those two. So we need to know how much is the shear stress changing as we move in the x direction. So we're interested in di-tau di-x, rate of change of shear stress with x. That'll be di by di-x, the rate of change with x of mu di-w di-x. That's the shear stress. Take the derivative and we get, if mu is a constant, mu times di2w di-x squared. And that's question 3. Question 4 said we have a gate here that's holding back water by carrying a moment load at its base. So this gate's sitting here and the water's on this side of it. If it wasn't rigidly fixed down here, if it wasn't holding that moment, it would just flop over like that and the water would all rush off this way. So there's a moment here at the base of the gate that's holding the gate in place. So that's that moment there. And it's got to be acting in this direction against the water pushing in that direction. The width of the gate varies as an unspecified function of the coordinate dimension x. So width is some function of x. Where's x? There's the x-axis. So the x-axis extends like this, conveniently already drawn along the surface of the gate. So it's a varying distance into the page is the width of that gate. Write an equation for the pressure on the underwater portion of the gate as a function of x. So that's that region in there. Well, we should working gauge pressure. Just to make life easy, because then P equals 0 in the air. And right here at the surface, the pressure is equal to 0. At x equals 1. And P is equal to 0.8, so rho GH will be 998 times 9.8 1 times 0.8 at x equals 0. So pressure is a function of x. When x is equal to 0, it's 0.8 times rho g. And when x is equal to 1, it's 0. So minus 0.8 rho g times x. Or 0.8 rho g times 1 minus x is the pressure. So it's a distributed pressure acting like that. Write an equation for the clockwise moment about the origin due to water acting on the gate. Neglect the weight of the gate. The equation should be an integral in x. Simplify, but do not solve the equation. So if we take a little element of area there, that little element of area is going to be dx in this direction along the x-axis, and it's going to be w wide. So w of x times dx is the little area. The pressure acting on the area is P of x, and it's acting in that direction, so it's creating a clockwise moment. So it's a positive clockwise moment. And the distance away from the origin is distance x. So the moment is the pressure force times the incremental area dA, which is wx dx, times the distance that it's away from the origin is x. That's for the little incremental area. And we have to integrate from x equals 0 to 1. If we do some substituting in, we'll get the integral from 0 to 1, x times P of x, so 0.8 rho g 1 minus x times w of x dx, or 0.8 rho g integral 0 to 1 of x minus x squared times w of x dx. And I don't think I can simplify much farther than that.